in the next section, we are going to get into the conceptual description of propagation of uncertainty. Suppose we have constructed a model to predict some quantity, such as the concentration or a worker's exposure. And we have identified that the various parameters of this model, so for example, the generation rate and the ventilation rate in the well-mixed room model, they have uncertainties in their values. How can we propagate these uncertainties through the model to discover the uncertainty in the model output? Because if we can do that, then this will provide us insights about the relative importance to our conclusions of various assumptions and uncertainties in the model inputs. And it can also help us decide whether it's worthwhile gathering more information to reduce uncertainty. So let's start simply, and we'll consider a model represented by a function f with only two inputs, x1 and x2, and one output denoted by y. And we will initially consider a discrete set of values for each of the x1 and x2 variables. So both x1 and x2 can take three values each, low, medium, and high. Of course, the low, medium, and high for x1 is different than the low, medium, and high for x2. So if we want to investigate the possible interactions between the effects of all the inputs at various levels, we'll have to look at all possible combinations of input values. So x1 can be low, medium, high, and x2 can be low, medium, high, which means we'll have 9 possible combinations. So y, the output variable y, can have 9 possible values. Now we can extend that example a little bit more by making it quantitative. And so x1 can take any of three values, 0.3, 1, and 1.7, corresponding to low, medium, and high. Except now we also assign the probability of each value occurring. So the probability that x1 can take a value of 0.3 is 0.2 or 20%. The probability that x1 can take a value of 1 is 0.6 or 60%. And probability that x1 takes a value of 1.7 is 0.2 or 20%. So the three probabilities, 0.2, 0.6, and 0.2, they all add up to 1 or 100%. Likewise, x2 can take three values, 0.5, 1, and 1.5, and these correspond to probabilities of 0.33, 0.34, and 0.33. Again, these three probabilities add up to 1 or 100%. So now if we look at the values of y, let's just look at the first value at the top, which is y equal to 0.8. And this occurs only when x1 equal to 0.3 and x2 equal to 0.5 with their respective probabilities. And so y equal to 0.8 will occur with probability of 0.2 corresponding to x1 and 0.33 corresponding to 0.5. And so y will occur with a probability of the product of these two probabilities. That is 0.2 times 0.33 or 0.066. Likewise, the second value, y is equal to 1.3, will occur only when x1 is 0.3 with a probability of 0.2 and x2 equal to 1 with a probability of 0.34. And so the probability of y equal to 1.3 is 0.068. And you can similarly calculate the probabilities for each of the other combinations of x1 and x2. And these are listed on the far right-hand side of the slide. And if you add up all these probabilities, you will also reach a value of 1. So the probabilities always add up to 100%, whether we consider x1 by itself, or x2 by itself, or y by itself. So that's great, but there are some limitations to this approach. So we considered a very simple example of two variables with three levels each, low, medium, high. And so we end up with 9 possible outcome levels for y. What if we had 10 variables with 3 levels each? So now suddenly we have 3 raised to the power 10, or 59,000 branches coming out on the right-hand side of that probability tree. But even that is an underestimate, because very often uncertain quantities that we encounter in modeling are continuous and not discrete. We don't necessarily always work in low, medium, high. So we may more naturally use probability density functions to represent the input parameters. And it's usually very difficult to obtain analytical expressions for the output in such cases. And so one way to deal with this problem is to select a moderate-sized random sample of scenarios for evaluation, and this is called Monte Carlo sampling. And each scenario is generated by selecting each branch at a node according to its assigned probability. And the branch values are generated from the underlying continuous probability distribution. Now, if that sounds confusing, hopefully it'll become clear when we run through some examples. So as the first example, this is from a paper by Mike Jajak from 1997. This paper describes the use of Monte Carlo simulation for a very simple model that we are familiar with, the well-mixed room model in the steady state, where the concentration is the ratio of the generation rate to the ventilation rate, G divided by Q. The traditional way of doing uncertainty analysis is that we assume that data is available on the value of G, or the source, and the data for G are normally distributed with a mean of 50 milligrams per hour and a standard deviation of 5 milligrams per hour. And before people started doing Monte Carlo uncertainty analysis, they would go about doing it this way. They would say the worst case is when we are 3 standard deviations greater than the mean. Worst in the sense this will lead to the highest exposure. So 50 plus 3 times 5, so 65 milligrams per hour. And the best case is when we are 3 standards below the mean, so we are at 50 minus 3 times 5, or 35. Just to make things interesting, we'll assume that for Q, no measurements are available, but we can estimate from existing literature that the ventilation rates has never been observed to be below 0.2 air changes per hour, and it has never been reported to be greater than 30 air changes per hour. We don't know what the situation is in this particular setting, but we know it's somewhere between 0.2 and 30 air changes per hour. And so the worst case is 0.2, the best case is 30 ACH. So we can run the model and say in the worst case, we have the highest value of G, which is 65, and the lowest value of Q, which is the 0.2 air changes per hour, which for this particular room turns out to be 3.6 cubic meters per hour. And so we get a value of concentration of 18 milligrams per cubic meter. The best case is the reverse. So the value of G is the lowest that we can imagine, which is 3 standard deviations below the mean, or 35, and the highest value for Q, which is 540 cubic meters per hour. And so the best case scenario is when the concentration is 0.065 milligrams per cubic meter. We can simply show our estimate of the model output and the uncertainty around it using this simple error bar. The problem with this type of approach is that we are arriving at the worst and best case scenarios by combining 2 very low probability events. So the worst case would occur when G is the highest and Q is the lowest, and both these low probability events need to occur at the same time. And these will probably not happen very frequently, or they would actually happen very, very, very rarely. And the same thing is true for the best case scenario, where we have the lowest value of G and the highest value of Q. So for both of these events to occur simultaneously is very rare. And so we end up with the uncertainty limits that are too broad to be realistic. A more realistic approach is provided by this Monte Carlo analysis. And what we do here is, rather than just take the ends of our probability distributions, for example, for the generation rate, we took the values as 35 and 65 and ignored all the values in between. Now we are going to take the entire normal probability distribution with a mean at 50 and a standard deviation of 5. And likewise, for ventilation rate, we take the entire range of values between 3.6 and 540 cubic meters per hour. And what we now do is we obtain 10,000 independent samples obtained randomly from their respective probability distributions. So, for example, we would go to the distribution of G and randomly obtain one value of generation rate. And we'll go to the distribution for Q and obtain one random value from the distribution of Q. And we'd use the model, divide G by Q, and obtain one value of C. And then we do it a second time where we again go get another random value of G and Q, divide one by the other, get a different value of concentration. And we do this a large number of times, 10,000 times in this example. And now at the end of this, we'll get 10,000 values of concentration C, and these can be now plotted as a probability, as a histogram, and these provide us a probability distribution for C. So when we have 10,000 values of C produced by this Monte Carlo sampling approach I described, we can plot these 10,000 values as a histogram shown as blue bars in this histogram here. And we can then calculate the mean of these 10,000 values. So that comes out to be 0.46. We can calculate the median, that's 0.19. And we can also calculate the 5th and 95th percentiles by just arranging these 10,000 values from the lowest to the highest and finding the 500th value, that would be the 5th percentile, and then the 9,500th value, that is the 95th percentile. And we can see a couple of things right away. The first thing, which immediately is striking, is that we look at the shape of this histogram, and it looks very much like a log normal distribution. And it looks skewed with the minimum at 0, and then we have a long tail, very much like a log normal. And this shows that when we have any kind of variation in the values of G and Q, and we had randomly picked a normal distribution for G and a uniform distribution for Q, we end up with a log normal distribution for the concentration. We end up with a skewed distribution for the concentration that can be described as a log normal. The second thing we notice is that the range of variability here, for example, we can look at the distance between the 5th and 95th percentiles. It's 0.09 to 1.54, which is much, much narrower than what we had obtained by the simple worst case, best case scenario, where the highest concentration that was predicted was all the way at 18. So we have reduced the uncertainty in our estimates by almost one order of magnitude. So now we have the results of the Monte Carlo uncertainty analysis, and I'm just pictorially showing the concentration as a ratio of generation rate to ventilation rate. But now, instead of point values or point estimates for G and Q, we have distributions for G and Q, and we end up with a distribution for C. One of the advantages of doing Monte Carlo analysis is that we can do what is known as a sensitivity analysis. And this essentially shows how much the uncertainty in each variable contributes to the variability in the output. And this can help decide where to allocate resources to reduce uncertainty. So in our simple example, we can do a sensitivity chart, and this, without telling you how it's done for now, I'm just telling you the results of this. So we have two variables, the ventilation rate and generation rate. And what the sensitivity chart is telling us is that 97.9% of the variability in the concentration comes about because of the uncertainty in ventilation rate. And only 2.1% of the uncertainty in concentration results from uncertainty in the generation rate. And when we think about it, it makes sense because the ventilation rate is one thing we actually don't have any measurements about. And so we have this very wide uniform distribution ranging from 0.2 all the way up to 30 air changes per hour. And this is basically the range that has ever been observed in the published literature. And clearly, it could be too wide a range to describe the ventilation rate in our particular scenario. The generation rate, on the other hand, is very narrow, and we know it very precisely, and we know that it's the mean is known and the standard deviation is known. So it contributes only 2.1% to the overall variability. So how can we use this information? So if we wanted more precise estimates of the concentration, would we go and say, okay, let's narrow down the ventilation rate estimate, or should we narrow down the generation rate information? Clearly, it's the ventilation rate where we need more information, and that's where we need to spend our effort and resources and money, and not on nailing down the generation rate further. And so if we now compare the simple model, the best case, worst case model versus the Monte Carlo output, we can see that it produces a much narrower uncertainty estimate and more useful, I would argue, uncertainty estimate. I want to end this section by talking about one more thing. So let's assume now that for this particular scenario, we actually obtained 3 samples, which is not an unusual sample size. So 3 is a very common sample size in industrial hygiene. And we obtained 3 values, 0.09, 1.75, and 1.46. Now, if we look at these 3 values and we look at the 95th percentile of these 3 values of this distribution, and if we look at the 95th percentile of the log normal distribution from which we assume these 3 values came, that is 9.45, and you can see that the upper tolerance limit of the 95th percentile is goes all the way up to 200,000. So if we compare the 2 modeling outputs versus the result of exposure assessment based on just our monitoring data, we see that, in fact, the Monte Carlo and even the simple best case, worst case model produce narrower estimates of the exposure than a few limited monitoring data. We have always assumed that monitoring data are the gold standard and more reliable than modeling. But in fact, I would argue it's the opposite. Modeling results are much more useful and much more certain than the results of small sizes of monitoring data.